A single neuron in a neural network can see cats, cars, and snouts at the same time. Here is how one independent researcher finally untangled what it is actually looking at. In the world of mechanistic interpretability, one of the most famous puzzles involves a single neuron that activates on entirely unrelated things. The neuron at channel 55 in layer mixed 4E of the Inception V1 image recognition model has been known for years to fire when it sees cats, when it sees car snouts, and surprisingly when it sees full cars. This phenomenon is called polysemanticity. And it means a neuron is not a clean concept detector. It is a messy bundle of multiple patterns sharing the same weights. The question is, can we untangle that bundle and figure out which pattern the neuron is actually responding to at any given moment? An independent researcher named Hariam Narang has published a new paper attempting exactly that, using a method that turns out to be surprisingly simple. Instead of using activation space as a marker of what concept a convolutional kernel has found, Narang tags every pattern the neuron sees across examples by clustering the Hadamard product of each high-attribution receptive field with the kernel weights. In plain terms, the Hadamard product is just element-by-element multiplication between the receptive field and the weights. This gives a weighted view of what the neuron is actually processing in each region of the input. By clustering these weighted patterns together, each cluster reveals a distinct concept the neuron detects. This is different from the traditional approach of feature visualization, where you optimize an input image to maximize the neuron activation and hope the result tells you what it looks for. Narang calls his method a simple procedure that provides substantial disentanglement. The results are striking. Along with the familiar clusters that feature visualization had already hinted at cats, snouts, and cars, Narang finds a large number of additional clusters that were previously unknown. Letters, human faces, salamanders, and many more concepts emerge from the clustering. Some of these are high-valued activations that the neuron fires strongly on, while many others are low-valued clusters that contribute only a small amount to the final output. This raises a fundamental question about what it means for a neuron to be activated. Is it simply a high positive activation value? The paper shows that all the substantial input signals come from maximum activating clusters, providing evidence for the hypothesis that a neuron is truly activated when it emits a high activation value. But the sheer number of clusters suggests the neuron is far more complex than a simple concept detector. To understand how the neuron decides whether something is a cat, Narang examines how previous layer neurons activate for cat face-like concepts. He finds that many neurons in earlier layers activate for cat faces and also for dog faces, each contributing non-trivially to the final output of the mixed 4E neuron at channel 55. This means the cat detection is not coming from a single clean signal, but from a distributed pattern of activation across many previous neurons. Some of these previous layer neurons fire on cat-like features, others on dog-like features, and they all feed into the same polysemantic neuron. The neuron essentially acts as a convergence point for multiple overlapping concept detectors, each pulling it in a slightly different direction. The most peculiar finding in the paper involves the low-valued clusters. Narang discovers that clusters associated with letters have all their dependent neurons also firing on the same letter concept. Even more interestingly, the positive and negative weights are evenly distributed between these dependent neurons, effectively bringing down the sum. This is evidence that gradient descent is working deliberately to push certain patterns into a noisy, low activation range. The neuron has learned that letters are not important enough to deserve a strong, dedicated signal, so gradient descent has distributed its weight evenly across multiple neurons to keep the letter detection weak but present. It is a subtle but powerful insight into how training shapes what neurons actually encode. Despite the quality of the work, the Reddit post in the machine learning subreddit received almost zero attention, with 0 score and 0 comments initially. One commenter called it sad that such work gets no attention, assuming it is not attractive for funding or achieving state-of-the-art on benchmarks. Another pointed out that mechanistic interpretability is actually a hot field, with oral presentations at NeurIPS. A commenter named Oli266, who is also working on mechanistic interpretability, asked a sharp question about whether the low-value letter clusters show genuine polysemanticity or are just noise from gradient descent not bothering to clean up rarely activated patterns. They also expressed curiosity about how the method holds up when moved to language models, where attention heads tend to be messier than convolution filters. Another commenter suggested using this approach for detecting model biases and alignment. This work is notable for several reasons. It is one of the first papers to apply mechanistic interpretability techniques to a convolutional neuron in a classic image model, rather than the more popular transformer architectures that dominate the field right now. As one commenter noted, it is rare to see mechanistic interpretability work on a non-transformer model. The method itself is elegant in its simplicity. Cluster the Hadamard product of receptive fields and weights, and the neuron's hidden concepts fall out naturally. It sidesteps the need for a full feature visualization pipeline while still providing substantial disentanglement for independent researchers working outside of large labs. This demonstrates that clean mechanistic interpretability work can still produce meaningful results without massive computational resources. If you are interested in mechanistic interpretability, check out the full paper linked in the description. The author is working on language models next. Let me know what you think in the comments and subscribe for more deep dives into AI internals.